See if it works first try this time. Share my screen. Looks like it's recording. You are recording. All right. All right. So any questions to get started with? Gotta load up a file here anyways while you're thinking. Fields. Transformers. Transformers and copy. There we go. If you're thinking there's more than meets the eye, there probably isn't. It's not too bad. So the last one we did was induction. Are you finding the questions? You can analyze them based on the left-hand, right-hand rules business. The solution sets are kind of what you'd expect, hopefully. Let's just put it this way. That's what I'm assuming based on there not being any questions asked. So
yeah, I guess. It's a bit confusing at times, but try to figure it out.
We're trying to like do it all virtually all just drawings, right? So I you notice probably that I put I think I in that one or the previous homework assignment anyways, I put a picture of my actual hand to try and clarify what I was trying to draw. Yeah, feel free to ask if there's any questions, but otherwise let's just get transformers out of the way. It would be silly to get this close to talking about something that has such an important application in the world around you without actually nailing it down. The grade 12 book and the grade 12 lesson yesterday talked about how there was a slide that I said I'm going to do more on this tomorrow, right? But it was like if you had a Faraday ring where the number of turns on one side is not the same as the number of turns on the other, then it actually increases or decreases the voltage. But that was, like pretty much it. And it's such an important application. I want to do a little more job, a little bit of a better job talking about it. So this is it. Okay, transformers, and it's a further use or application of Faraday's ring. So this Faraday's ring here has a coil on this side. We can call it the primary coil, and we can call this one secondary coil, but you can use them either direction, right? So the primary coil is the one with the voltage applied. So this one here, we're going to say, like, just point out that whatever we call the primary coil, I'm almost put it in quotes here. Let's go with something a little more visible, like the purple. So in quotes, really, I'm just saying like that's the one with the applied voltage. Okay. I can't really say anything about the secondary coil yet because I have to talk about it. Okay. So what happens is when current flows through the primary coil, we know a magnetic field is going to be induced, of course, right? It's going to make a magnetic field. So a magnetic field is produced, and then an equal magnetic field is produced in the region of the secondary coil due to the ferromagnetic material, the properties of the ring. Okay, so basically, if we had a north build on this one, let's say because of the electron flow, let's go with purple some more here. If I had electrons flowing like this, and so on, I don't need to draw all of them, but it just feels good. So I'm just going to use my left hand. I'm going to curl my fingers in the direction of electrons flowing, and so my thumb's pointing up, right? So this makes a big north pointing up. I'm just going to make that a little thicker and bigger and easier to see. So that's just the left-hand rule for, we should have drawn the N in advance here too. N, make it bigger and easier to see too. So anyways, that's the magnetic field that's going to be induced, right? And so you're going to end up with a magnetic field everywhere, like in that iron, right? This whole iron ring is going to become a magnetic, So, yeah. Anyway, so if that happens, the next step here is then to say, as this magnetic field builds, N falls, right? Voltage that causes current is going to be induced in the secondary coil. And we know that the electron flow or current, however you want to describe it, will be opposite. It'll cause a magnetic field that's going to oppose the change. So basically, as the north is building like this, you're going to want to create an opposing north like this. Right? So you're going to have a north induced there that's going to oppose the change that was causing it, right? So then that would mean, I guess, that electrons would be flowing the other way in the coil. Now, the direction of that electron flow, although we're predicting it and so on, doesn't really matter, of course, because if electrons are flowing in the other coil, you've got electrons flowing in the other coil. You've induced electron flow. You can use that energy for something at this point. Okay, so that's the main Lenz's law idea of what's going on. The next step is to sort of talk about what effect this 4 turns on one side and then 8 turns on the other has. And notice that we're talking about like twice as many turns, right? So times 2 for number of turns. The amount of electromagnetic force, EMF, right, or voltage, right? So let's just remind ourselves we're talking about voltage induced depends, of course, on the strength of the field that's changing, which is the same on both. It depends on the speed at which it changes, which is going to be the same on both. And it depends on the length of the wire in the field, which is very obvious based on just logic and previous things we've talked about, right? So it turns out that if the secondary coil has n times as many windings, so in this case, n is a 2, right? So just put it like a 2 beside it in this case, for example, then the voltage induced on the secondary coil will be n times as much. So will be n times as much as the voltage on the secondary. So basically, if I put, say, 10 volts here applied, then it's going to turn out to be twice as much. It's going to make 20 volts induced. I have to spread my word out here. So that'd be 20 volts induced. Go ahead.
Sorry, that was just the dog turning it on. No, I didn't.
No problem. So just wasn't sure if you had a question or not. That's also, here we go. So that means, see how this is functioning as what they call a step up transformer. Okay, because we're going from 10 volts applied to 20 volts induced. So that's going to be called a step up transformer. Just trans for short because I didn't have room. Okay, and I want to just explain a little bit more about that. But you certainly can tell that the applied force can be, applied voltage can be doubled and make the voltage induced be twice that of the voltage that was applied, right? So it's called a step-up transformer. So let me make that more visible for everybody for a little bit of time for you.
Mr. Wood, I have a question. When you're talking about Lenz's law, if the voltage is applied like the whole time, will the secondary charge always be induced?
Sorry, he was away from the computer for that.
Okay, I thought so. I wasn't sure.
I had to grab a drink of water. That's all. My voice was cutting out on me. So the voltage is only induced on the secondary coil when it's changing, right? So just like Lenz's law, like while the north is building, it's going to make a north to oppose it, and then as that north is fading away, it's going to make basically a north the other way to try and fight that change. So it's only when it's changing.
Okay.
So we need to, yeah, it's in here, right? So so when a current flows, a magnetic field is produced. This part's fine. It's always there. Like a magnetic field is always produced, right? But it's only as this magnetic field builds and falls. So it's that change, right? So that's an important part for sure that you're asking about. All right. So just a note about what we talked about recently, right? With the alternating current, the current direction continually changes, right? And so the magnetic field is continually like building and then falling, building and then fading or whatever. So with a transformer, that's perfect because then the alternating current is continually induced in the second coil as the magnetic field is continually induced to oppose that continually changing magnetic field produced by the source, right? So with AC, transformers continually produce energy on the secondary coil. They're really transferring the energy from like the applied to the applied coil to the secondary coil, the primary coil to the secondary coil. In contrast to this, DC current, which was originally the kind of current that people preferred, DC is just sort of simpler to understand, right? It's very easy to understand the idea of energy being picked up by a battery and brought to a load. And it was the first one that people knew about. You could put lead and lead acid batteries have lead and nickel or something. Anyways, they have lead plates inside of acid. You can make a constant voltage causing direct current. It's just basically the old school battery, right? That we still use today. So anyways, that produces direct current. So people just felt more comfortable with it. The problem with direct current, of course, is that you're only going to get an induced, higher voltage if you want higher voltage, which we're going to talk about why we want higher voltage soon. But if you want this higher voltage, you'd only be getting a pulse of higher voltage when you close the switch to make the magnetic field build, and then when you open the switch to make it fall. So while DC current is connected, the magnetic field is not changing; it's steady, and so there's not a magnetic field induced, and so there's no current induced. So DC is no good for transformers. You have to have like a physical switch that would be turning on and off using energy the whole time. Okay, so AC is the way to go, of course. Very obvious now that we understand things, but there was a pretty big and hotly contested debate back in the day, and DC had been developed a lot by Edison, and so Edison had a bunch of patents to do with DC and had a bunch of money invested in it and really wanted to convince people to use DC. And then there was people that were learning about the science of it. Tesla was one of the guys, and so he was saying like AC is the way to go because of this. And there was a lot of misinformation back then. The DC camp tried to convince people that AC current was dangerous. And it's actually the other way around. DC current's the more dangerous one. If you look at DC 120 volts in comparison to AC 120 volts, DC is way more dangerous. Actually the 120 AC current is alternating, right? And it peaks to higher than 120. But when we talk about 110 or 120, we're talking about the RMS. It's called the root mean square average. So basically the average voltage. When the voltage is fluctuating back and forth, what's the average? And that's your voltage. And so you can see you're going to have, you actually have less power or less voltage available with alternating. And it's inherently less dangerous because of the high frequency it's at too. You've seen me play around with high voltage stuff in 124, the Tesla coil and things like that, I'm sure. And it's like it's 400,000 volts. And you don't get electrocuted because it's high frequency is one application, and also there's not much energy available. So that's going to link to this soon too, the idea of how much energy is available. Anyways, let's move on. So just to be more clear about this number of turns thing, if it's not as obvious going from 2 to 8 that it was at times 4, or in this case, what was it? 4 to 8, so it was times 2. And you can see we have, the number of secondary turns divided by the number of primary turns. So you're going to have like an NS over NP idea, and that's just the multiple. It's not hard. Okay. So if you had an odd number of turns, like if you had 7 turns here and then 311 turns here, you'd be like, oh, 311 divided by 7 gives you the multiple. It's very, very mathematical, very simple. So what we've shown is that a voltage of here, of this number to this number, technically it's not actually 10 to 10 or whatever, but if it was, as we had before, if this was 10 and this was this would be 20, just like we showed, right? Because it was times 2. Depending on I guess it could be a peak of 10 and then it would be a peak of 20. We just wouldn't call that 10 volts. That would end up getting called like 7 volts or something, whatever that RMS average is. So if you're looking at household voltages 110, the peak is actually higher than that. Anyways, so that is, of course, what we looked at, right? So if we wanted to talk about a step down transformer, it's just the exact opposite, right? We're going to call this one the primary this time. We're hooking up to this side. So if this is the applied voltage, then this is your primary. Instead of actually physically turning the thing around, I'm just pointing out that we're using it in reverse, right? So this is your primary, and this is your secondary. And then, you're just ending up with your multiple the other way around. A 4 divided by 8 means a times by a half. This relates to the ratios discussion of like second divided by first, right? So it's the second divided by first always to get your multiple, right? So your multiple equals second divided by first. So yeah, I'm always going to think of that as NS divided by NP, second divided by first. Yeah, so that you can see that working as a step down transformer. And I do want to show as well just a little bit of a justification of the idea of this. If you're picturing the voltage that you get from each one in order to induce the amount of voltage that must be happening right in this wire in order to have the electrons move the way they are, and then in this wire to get the electrons move the way they are, all the way along all these voltages here, right? Picture the amount of voltage necessary in each spot of the wire to make the electrons move the way they are. And then you look over here and you're like, oh, wait, we're going to have twice as many, so you can really picture this where you add this all up and you end up with twice as many, right? So that's the idea of this twice as many thing. So you can really picture the logic of how this works, that you get this extra voltage, okay? Because the voltage induced on each coil has to be appropriate to make the magnetic field. So if we have, this is an example that I would definitely have to be careful with, by the way, actually playing with. So the multiple in the number of coils, right, equals the multiple of the voltage induced. And I'm just noticing that my words are backwards here. So multiple in the voltage induced is equal to the multiple in the number of coils. That's now exactly what we've been talking about. So in 124, there's a bunch of different coils that have a bunch of different numbers of turns. So if we were playing around with a 12-turn coil, which is that this one isn't, but there is one. It's much thicker looking copper wire. You can literally see, I think it's actually 9 turns or something, but I'm just doing easy numbers for us here. So if we had a 12-turn coil and a 12,000 turn coil, you can tell right away that the multiple we're talking about is 1,000, right? We're talking about times 1,000 here. And of course, when we put the numbers in, you're going to have like a 12,000 here and a 12 here. So there's your 12. There's your thousands, right? So we have here the voltage of the primary that we're applying is 9 volts. That's your applied voltage. Right, that's on the primary. And so your secondary voltage is from this equation. So we have secondary voltage divided by 9 equals 1,000. We're going to multiply both sides by 9. I have a feeling I'm ahead of myself, and the next page is going to be redundant and show this. But why not just go for it here? So what we're getting here is we put a 9-volt battery across here, a little pulse. You know, as soon as you connect it, then that's 9 volts connecting there. That leads to over here 9,000 volts. So if your fingers happen to be touching that, you get a shock. It's quite actually shocking, literally. It's you know, you have to be a little bit careful playing with this, right? Caution does need to be used when playing around with these. But you know, are you going to die from this? Right? Think about it. You know, is that 9,000 volts? Can it be as dangerous as you'd think? Because 9,000 volts will kill you in certain applications, right? Like if you're playing around with wires and from a hydro line and it happens to be 9,000 volts, yeah, you're going to lose. Not only you're going to die, you're going to lose your arm. You're going to lose half your body. You're going to vaporize. Like it's very, very powerful stuff in that application. But in this application, we're talking about a 9-volt battery, one little 9-volt battery. Is that going to vaporize half your body? Lovely thought, I'm sure, right? But you just don't have that much energy available. So you need to consider the fact that transformers are not producing energy. They are literally transforming the energy. Okay, so they're not producing energy, they're transforming it. Right? So in this case, we're going from low voltage, that's the transformation, to high voltage. But something has to give. This is high voltage, but it's not more energy overall. Okay, so not more energy per second, let's say. Per second. But what's happening here is this is just more joules per coulomb. Each coulomb carries more, right? So if we relate it back to what we understand about current and so on, you can put here that each coulomb carries more. Each coulomb has more energy. So if we say we can't possibly have more energy than we started with, right? And each coulomb's carrying more energy, what does that mean about the electricity in that secondary coil? If we have more energy per coulomb, but not more energy overall, I'm hoping you're leading to the assumption or the conclusion here that less coulombs would flow, right? So if we don't have more energy, we get less of them. So, but less flow, right? So yeah, each coulomb's carrying 9,000 times, 1,000 times as much energy, right? So let's put numbers to it, right? In the example we've talked about here, let's go here. So each coulomb here has 1,000 times as much energy. So joules per coulomb, right? But as a result over here, we've got 1,000 times less current flowing. Does that make sense? Can you picture how that would work? Like it's just a different form of the energy, right? High voltage, low current instead of, overside we would have had low voltage and obviously higher current. So that's the logic worked through about it. Mathematically, of course, is an equivalent, right? We say conservation of energy, the amount of power in equals the amount of power out. Power is just the convenient way of talking about this because we have a formula for power, right? So we have power P equals VI. Yeah. So we got P equals, reminder, power equals VI, right? P equals VI. So we can say the voltage in and the current in. So in is like the applied stuff, right? On the primary coil. That has to be equal to the voltage out and the current out multiplied. And by the way, this is an ideal, this is where it says actually over here. Over here it says P equals VI, right? This is, by the way, an ideal transformer where no energy is lost. Okay, so this is if no energy is lost. To heat, etc., right? Inefficiencies. Of some sort, usually just heat though, right? So it's an ideal transformer. So in another, like you could talk about inefficiencies as well, and say, oh, we're losing 10%, whatever. There was a lesson last week or a week before, whatever, where we were looking at the voltage and current and whatever information on power supplies, like the CSA tags on electrical equipment, and the laptop cord was surprisingly inefficient. Like the amount of power that was being supplied in was a fair bit less than the amount of power that was being supplied out, like way more than I would have thought. Transformers, I would have said before seeing that particular set of numbers, I would say they lose very little energy. But that laptop one certainly is losing a fair bit. But the more you're losing, of course, the more heat you're producing. Right? That's the quote unquote lost energy. It's to heat. It's just not attainable anymore. It goes away out into the universe, if you will. It's not lost technically. It still exists. Is what I'm talking about. We're not creating or destroying energy. We're just transforming it to other areas. So I'm just solving here. I'm dividing the voltage out. So the voltage you get off the secondary coil, I'm dividing that out. Then I'm dividing the current out, and I'm ending up with this equation. Is that we have this voltage in divided by voltage out equals the voltage or current out over in. So notice that this one, you need to notice that the current over current is flipped. And you got to watch that, the out in business. And I feel like if I were to rejig this slide, I would just make this be all the ins be P's. So this could be P, P, and this could be S, S. And this would be obviously S. And this would be in is primary. All the ins are primaries. Okay. If it makes it more the same as the other stuff, I just didn't notice inconsistencies. I apologize. So the out is the secondary one, out is secondary, out is secondary, out is secondary. So if you want to do it with S's and P's instead, we end up with this formula. Now, is this formula down here S's and P's to match the N's that we had? Yes, it is. Excuse me. All right, so they transform the energy. They're going from low voltage to low voltage, high current, switching to be high voltage, low current, right? And vice versa, of course, right? So you can happen, the transformation can be this way, or it can be this way. But either way, it's this combo to this combo, right? We're going from one to the other. That's what transformers do. So for example, with a device that you're plugging in, like a computer, they don't run, the motors and the chips and whatnot in computers don't run at 120 volts. They actually run typically at like 12 volts or 18 volts, things like that, just because they function better at those voltages. So you have a transformer in the back of your computer, and it's certainly in the power cable for your laptop, that just transforms the voltage of high voltage, low current, actually, in the case of your house, right, to being lower voltage but higher current in your computer, the thing you're plugging in. Okay, so that's one application of transformers, is just changing the current and voltage combination to be what you need it to be for the device to run properly. So that's certainly one application. Yeah. So back to that 9,000 volt transformer. If we were playing around with it in 124 and getting shocks from it, it's not fun to do. I'm actually kind of scared of it, to be honest. It's nasty. But if we looked at the numbers, we'd have what? An applied voltage on the primary coil of 9 volts. And we'd have that secondary voltage that we know is going to be 9,000. So at this point, I could say we're going to figure it out, I guess. Or do you want to? Depends what you want to do. We already did this part. Let's do this. We already did this part. So let's just remind ourselves. So secondary coil was the 12,000. primary coil was the 12. And so this led to Vs equals 9,000, right? So that's what we've done already. What you do is then you say, oh, okay, well, let's work with the other part of the equation. And we say, okay, for that one, we've got the number on the secondary is still the 12,000. And the number on the primary is the 12. And I guess we'd have to state I'm just going to do this for now at least. So the primary and the secondary here, if I'm looking for what the secondary current is going to be, right? If I'm looking for what that amount's going to be, then I guess I'm going to solve for it. Let's do the easy math flip trick, right? Where we flip up and upside down everything. So 12 over 12,000. You can get away with that if you just have two fractions that are equal to each other. You can't get away with that if you had like a fraction plus a number. You can't just flip it, right? But if you don't have that extra number, then you can just flip it. And then all I have to do is multiply both sides by the primary current. And you can see what we're getting here, just ideas wise here, is this current on the secondary coil is going to be the primary, whatever the primary current was, but multiply by over 1,000, right? So it's divide, right? i.e. 1,000 times less. So we got 1,000 times more voltage, but we turn from that, we get 1,000 times less current. Okay, so even though the voltage is very high, there's very little current, and so it's really not as dangerous as you think, even though it does actually kind of hurt a little bit. It can be quite, and that is unintentionally very literal. If we had an actual power rating, if we'd say that the power applied was 2 watts or something, then we could say, oh well, P equals VI, power rating of 2 watts, and we have this 9,000. Sorry, the applied voltage is just the 9, right? Let me undo a little bit here. That would just be 9 and I, and so we'd be like, oh, so we have current of 2 over 9, or if I wanted to make the numbers nicer, I'd be like, let's make it be 9 watts. So we have 9 watts, so that's like 1 amp flowing, right? You can tell that the amount of current that would be flowing on the secondary coil would be 1 over 1,000 amps, right? So 0 decimal whatever, right? So 0 decimal 1, 2, 3 0 zeros, something like that. So 1 amp on the applied side would lead to only 0.001 amp on the that's the maximum that would be available. So you can tell you're not in the zone there.
Mr. Horn, yeah. I think I missed something on the math there. On like the IP equation, how did you get it from 12 over like 12,000 to 1 over 1,000? Like in the second line there.
So do you mean like here?
Yeah.
That's just divide by 12. Like 12 over, actually I should go green here. Go green, it's better for the environment. I mean, it's clearer to see. All right, so divide by 12, divide by 12. Top of, I'm just converting to an equivalent fraction there.
Oh, all right, I just didn't see that. Okay.
Yeah. So, you know what, that's a little math thing along the way. And your brain is thinking, physics and concepts and understanding. And it's actually kind of hard to, get your brain to switch between the two. It's transference of math skills, right, is always a challenge in education for sure. So don't feel bad. But yeah, once you see it, you're like, oh, okay, I know how to do that. I just didn't think of it in the context of this crazy stuff I'm doing. So totally normal. So you'll see it written like this, where you got primary winding and secondary windings and so on, right? Other examples here. So they're showing if you have 100 volts applied, first of all, let's analyze that, and it's 5 to 20, right? So you're like, oh, that's times 4, right? So check it out. There's your 400. This is just a Google image. We're just confirming that we're actually checking right now to see if they're right. I think of it as, right? Because it's supposed to be 4 times as much voltage, so there it is. What about the current? We know the current is supposed to be 4 times less, right? So divide by 4 gives you 2.5. So that's right as well, right? And then they have here, this is super ideal for sure, 100 watts, right? That's definitely the ideal, no energy loss. But of course, you know, put it in quotes because that's not really what happens, but it's close. Well, I thought it was close anyways. So with that lesson stuff done, what's this thing? You look at the end of your road, or look at the road in front of your house. You probably have one of these up on the hydro pole or the telephone pole, people call it, right? But of course, those poles don't just carry telephone lines; they actually carry electricity, and so those are, of course, transformers. So they are transformers. So what you have in here, let's just roughly sort of picture the idea of having a big coil of wire like this, right? That's there and it goes back up and out. So there's like an in and out for that coil. And then there's another coil in there. Let's make it like this. And it has sort of an in and out, you know? And so you've got these two coils that are beside each other. And so what you have is you have a line coming in, looks like it would be into the purple one. Actually, no, this depending on what this one's doing, it's probably a step down, right? So this is probably the red here at your road. Let's say maybe it's 5,000 volts. I forget what the number is. It varies anyways, to be honest. But that's the in from the road. Right, so 5,000 volts along the lines along your road, and then that steps down. See how they got lots of coils here to the, you know, the red one's lots of coils, and then the purple one's more less coils, right? So looks, I think it is anyways, looks like it to me. So then you're getting out of this, you're getting, you know, whatever it is, probably, you know, well, it's supposed to be 120, right, or 240, right? So that's stepping down to the 240 for your house, to the house. So that's a step down transformer if it's on the hydro pole outside someone's house. So that let's look at that. Why you would want to do this, right? Why do we want to step down and so on? Why was it at 5,000 volts in the first place? Really, what we're looking at. And so the answer to that is because less energy is lost when transferring long distances if high voltage is used. Because if we have high voltage, then automatically we end up with less current, looking at our power equation, right? And current forcing its way through wires. Let me just full size this thing because it's a little inefficient space here. Wires have some resistance, right? Wires definitely have some resistance. And so if you look at the amount of resistance in the wire, then you can actually calculate out the power lost to heat, right? And so you can tell that they were just putting the Ohm's law into that equation, right? So that's just Ohm's law. So notice we're jumping back to that stuff we first started with, which is pretty common, right? You end up learning that first stuff I covered was because I wanted you to be able to understand the importance of transformers. Anyways, so basically less current through the wires makes it so you end up losing less energy. This is just more specific about the amount of energy you lose per second, right? So what they do is they regain control of their computer screen. Wiggle the mouse, there we go. When you generate at a generating station itself, the generator, the water is turning, or the steam from the nuclear reaction is turning, or whatever, might be producing 20,000 volts, let's say, right? That's just literally just a motor. Remember, it's a DC motor being forced to turn, producing AC electricity, right? That's super easy. Motors were in use, and they're like, hey, check it out. If we turn this backwards, we make energy. So they're making, say, maybe 20,000 volts based on how fast the thing's spinning and whatnot, right? What they do is they step that up to 500,000 volts. Okay, so this is stepped up to 500,000 volts, which means way less current, right? And that makes it so you can transfer it from, the generating station in Pickering, for example, to your house, right? There's a nuclear power plant in Pickering that probably is supplying, 60% of the energy you use on a daily basis, right? So how do they get the energy all the way from there to here? Well, they step it up to a crazy high voltage. It's 500,000 volts. You don't want to touch that. So they step that down a little bit to 115 to a district transformer. Then they step it down again to 44,000 volts. Then they step it down to a substation. This is like the one in Crosby, for example. Right, so at Crosby, the wires coming out of there might be at around 4,000 volts. I said 5,000 here, but I'm just telling you, just talking ideas here, right? So at Crosby, if they step it down to 4,000, then the pole at the end of your road, at the road, sorry, in front of your house more so, right, will have the right number of windings to step us from 4,000 down to 120. Okay, so whatever that multiple is, you picture, that multiple is what the N over N is, the primary over the secondary. Whatever multiple is necessary to make that happen. And you can obviously tell that would be equal to the primary voltage over the secondary voltage, right? So you can tell what the numbers would be. That would be 4,000 over a 120. I'm interchanging between saying 120 and 240. I apologize for that, but that's just the houses have 240 and 120 available. So in this case, I was more honest about how it's actually 240. Here, when you use only half of it, like houses are wired, you're looking at 120. Don't let that confuse you, though. It's not that important. But basically, we went up at first to get less current, and then basically they gradually start to go down. Right, so this is down to a little bit safer, easier to handle, and then but you still have to transfer it. This is maybe going from like Kingston to somewhere, maybe I don't know, like whatever, and then it transfers even more to closer to you, and then it goes down a little more. So they kind of don't want the wires along the roads that might get hit in a car accident to be super high voltage, right? So they step them down to reasonable amounts for different areas. And eventually you get to what you get in your house. So that is transformers. And so again, you'll see I'm going to upload transformer homework solutions. The lesson itself, of course, will be PDF'd, and then you'll have the textbook pages to do with transformers. So I do want you to look through those and gain a full understanding of what transformers are and why they're important and so on. But now driving along the road, you see those canisters up on the tops of the towers, you'd be like, oh, there's that transformer. That's transforming the 4,000 volts along Highway 15 to that person's house. They actually have little big, I should say little, but they have big switches. So they have, I don't really see one here right now, but they'll have a big bar. Maybe that might be it there, but that bar can actually swing out. I don't see it on that one as well. So anyways, so during a major power outage, when they had the ice storm and all that, they went around and they opened all those switches so that as they were putting energy back into the grid, they could get the grid up and then gradually hook up each neighborhood basically by flipping those little switches. Yeah, so that's transformers. Now, I have to give you time to catch up. I have to, yeah, let me just, I think we're done there. And